We're learning to graph trig functions, and right now the focus is on sine and cosine functions. The standard form for a sine function is y equals a times the sine of bx minus c plus d. Now, some of these transformations you already recognize. A, whenever we multiply a function by something, is going to affect the height. So a is the amplitude. Let's leave b for a moment and do c and d. C is going to be a horizontal shift. Remember that horizontal shifts are opposite, and this is normal. We always see horizontal shifts somehow grouped with our domain. And D, number out by itself, is just going to be a vertical shift. Now, let's look at B. Ignore the orange. There it goes. Okay, let's look at B. B is going to affect the period of the function. So a trig function sort of looks like a spring almost, and when we affect the period, that's going to compress the spring, or it's going to like stretch it out. And how B does this is it affects the frequency of the cycles, or it affects the period, to the tune of 2 pi divided by B. So we'll get back to that in just a moment. Now, what I want you to do when you graph trig functions is to graph them very carefully. I want you to always use a piece of graph paper behind what you're graphing so that when you make these little marks on your paper, they're equidistant from each other. This is going to make it much easier for both me and you to tell if you have truly graphed what you intended to. Now, we're going to think about the parent sine function, and I know that my important it's easier for trig functions if I have denominations of pi, so I'm going to think in terms or in divisions of pi. Let's think. The sine of 0 is 0. The sine of pi halves is 1. The sine of pi is 0. The sine of 3 pi halves is negative 1. And the sine of 2 pi is 0 again. So this parent function for sine of x is just going to be a matter of connecting these important points in the way that I know that they connect. So in this case, see, we get a nice wave function. And all the trig functions are going to, or sine and cosine rather, are going to look wavy. And so just by knowing the shape of the sine function and where these 5 important points were, I knew how to get the parent function. Now let's add something else to this in another color. We're going to do f of x equals sine of 2x. Now let's think. If I put 0 in for x, 2 times 0 is 0, and I'm still going to have 0. So I put a dot at 0, 0, and then I think about pi halves. If I put pi halves in for x, I'm going to have 2 times pi halves, which is pi, and the sine of pi is 0 again. Now if I think about putting pi in, 2 times pi is 2 pi, and the sine of 2 pi is 0 again. So I have these 3 blue dots here, and I know what the shape of my sine 2x graph needs to be, but I'm not sure where to, I didn't manage to catch the peak and the valley there when I was, estimating points. So there are a couple ways to deal with this. One, I can think, what x value would I need to put in there so that I'm looking at the sine of pi halves, and so I think to myself, 2 times what would be pi halves? Oh, that's pi fourths. So if I put pi fourths in there, the sine value is going to be 1, and I know where to graph that point. Likewise, I can think, what value could I put in there so that 2 times the value gave me 3 pi halves? That value is 3 pi fourths, so I know where sine of 2x equals negative 1, and I can simply connect the dots. Now look at the effect that the 2 has on the sine function. It's compressing the graph, it's squishing it almost, and if you think about periods, if you think about the effect that this has, 2 pi divided by 2 just equals pi, and if you look at the graph from the beginning to the beginning of the next sine wave is the distance of pi. So this does change the period to this effect.